over Lewis acids and bases in the other video that I just did, but that video was getting too long, so I decided to cut it off and turn it into its own video, just because I think it'd probably be easier that way, and it makes more sense as its video on its own because it doesn't really have anything to do with the solubility effects that we were just talking about. So, a Lewis acid is different from a Bronsted acid that we've been dealing with, because the Bronsted acid donates a proton, right? Well, a Lewis acid accepts an electron. And then you have a Lewis base, which is different from a Bronsted base, which accepts the proton, because this one donates the electron. So yeah, with these, the way that you usually work them is you're going to have to draw the Lewis structure of what's going on, just so that you can see which one has a lone pair to donate and which one doesn't, so that it can accept it. So we're going to do a quick example where we have, let's say, ammonia plus boron tetrafluoride. And we have to label what the Lewis acid is and what the Lewis base is, as well as its product. So we're going to draw it out. So we do our Lewis structure for ammonia plus our Lewis structure for boron tetrafluoride. Yeah. And what does it yield? So we can see here that ammonia has the electron pair that it'll be able to donate to this boron, because we mostly deal with this in the central atoms, because that's where the lone pairs matter, just for this. So then since this one's donating the electron, this is going to be, this should be in purple, our Lewis base. And since the boron tetrafluoride is accepting the electron, this is going to be our Lewis acid. And our final product is just going to be this shared electron between these two, and just kind of its original figure. It's just that now they're happily sharing this electron. Yeah. So it's pretty simple just to see which one's donating the electron and which one is accepting it. But we can have more complex examples, like, oh, let me erase that because I kind of had this done before. But like I said, that video was taking way too long. So we can have another example where it's carbon dioxide plus water yields carbonic acid. And I say this one's more complex just because of how many steps it takes to do it, but it's still the same thing for identifying which is our Lewis acid and which is our Lewis base. So plus our water. So again, we can see that with our water, we have these lone pairs that can attach to this one. So since the water is donating the lone pair, this is our Lewis base, and this is our Lewis acid. So yeah, it's as easy as that. The only thing with this one is that you have intermediate steps, because yeah, this is going to attack here, which means that your carbon doesn't want to have another lone pair, so it's going to make that lone pair attached to this oxygen. So you're going to end up with a figure that looks like this. So you have your carbon with the double bonded oxygen, carbon, and then your kind of water structure attached to it, which yeah, it looks funky. Like, that's not how we're used to it, but it's just tracking the electron movement. So then one of these electrons is going to attach to this hydrogen, which will cause this double bond to break and form another lone pair on this oxygen, so that we finally get our Lewis structure of carbonic acid that we're used to, or at least that it looks right, you know? So then this just has the OH and the OH. But yeah, this is just a long intermediate step, but all you guys need to know is that this is my Lewis base because it's donating the electron, and this is my Lewis acid because it's accepting the electron. So yeah, that's pretty much it for Lewis acids and bases.